G'day everyone, welcome to Lubrication Explained. In this video, we're going to talk about the performance differences between standard mineral oil lubricants and polyalpha olefin synthetic lubricants. So as you're probably aware, there are two main classes of lubricants. You've got the mineral oils, which are derived from crude oils, and they comprise group 1, 2, and 3 in the API classifications. And then you've got synthetics, which fall under generally group 4 and group 5, of which the main category is polyalpha olefins, also known as PAOs. So these comprise the majority of the industrial as well as vehicle lubricants, and so it's a really important one to understand. So when we look at the base or raw material for a mineral oil, it's this. I've described it as a soup of different molecules. You've got paraffins, isoparaffins, naphthenics, you've got aromatic rings, so they're those benzene rings. It really is, if you like, a natural product. There's variability in it. There's variability in crude oils when you go to different places around the world, and refining is the exercise in selecting only the molecules with the properties that you desire. With synthetics, the raw base material that goes into manufacturing them is very regular. So I'm showing here decene, which is a molecule with a single double bond, but a chain of 10 carbon atoms surrounded by hydrogen. And that feedstock is very regular and very controlled. So it's a little bit like making plastics, for example. You're probably familiar with the idea that polyethylenes are synthesized from ethylene gas. So synthetic lubricants are exactly the same. Within the mineral oils, so they're the ones that are derived from crude oils, we can think of them as existing on a triangle of three different axes. So you've got paraffins, aromatics, and naphthenes, and as we refine them, we are starting to move from group 1, which has some aromatic content or aromaticity, as well as naphthenic content, and we're starting to move up the chain as we refine them further to a product which is predominantly paraffinic. Now, the advantage of group 4 or the polyalpha olefins is that they are pretty much exclusively paraffins. So they've got those really desirable properties. And the reason why mineral oils never get to this stage, it's not because we're limited by technology, it's actually commercial limitations. In order to make a crude oil look like and perform like a polyalpha olefin, it would just cost way too much. It would be cost prohibitive. And that's why we have synthetic lubricants. Now, if you were to compare performance characteristics, right? When I went through and talked about mineral base oil manufacturing, each of the different processes involved in making, in this case, a group 1 base oil, imparts different properties. And we can look at these and compare to a synthetic PAO to see why it's not necessary in the synthetic case. So, for example, the first one is vacuum distillation, and that gives us the properties of viscosity, flash point, and volatility. So vacuum distillation is us selecting the molecular weights that we want out of the crude feedstock. Well, with synthetics, what we can do to increase the molecular weight of the final product is we just let the reaction go on longer and we add more decene molecules to the chain. Right? So that's how we can get to a higher molecular weight. So we don't need the vacuum distillation process. Solvent extraction takes out the aromatic components and improves the oxidation stability of the product. But with PAOs, there is no aromatic content. So we don't need that stage either. We don't need solvent dewaxing, which improves our pour point and cold crank, because there are no waxy molecules in the feedstock. So there is no waxy molecule within our decene feedstock. And hydrofinishing is the process of basically cracking the weaker carbon double bonds, as well as removing nitrogen and sulfur compounds. Well, again, we don't have these in the raw feedstock for a polyalpha olefin. Now remember, this is for a group 1, so for a group 2 or group 3, we would replace that hydrofinishing with hydrocracking, right? Which is effectively doing the same thing, removing nitrogen and sulfur compounds, breaking double bonds, breaking open naphthenic rings as well. And again, we don't need that with the manufacturing of a PAO. So if we looked at the benefits, I'll go through a couple of these. First of all, what you're going to find out of a PAO is a higher viscosity index and better shear stability. So what do I kind of mean by that? Well, in a previous video, we talked about the viscosity index and it being a proxy for the way that an oil's viscosity varies with temperature. So if we were to, for example, take just the 68 weight lubricant, what a synthetic PAO might look like on this chart would be like this. So the variation with temperature would be less. Note that at 40 degrees, the viscosities are the same, because if I wanted to make a 68 weight, it's measured at 40 degrees Celsius. Now, why does this improve the shear stability? Well, it's got nothing to do with the inherent properties of the base oil. Shear stability isn't really a function of the base oil. It's more the fact that if I wanted to achieve a higher VI with a mineral oil, I would need to add in viscosity improver additives. And these additives are long chain polymers, which generally under high shear can break, right? And that's what reduces your shear stability. In a synthetic PAO lubricant, we don't need those viscosity modifiers, and therefore it is inherently a more shear stable finished product. We also have lower volatility and a higher flash point. So again, these two go together. And the way that you can kind of think of this is, if I were to look at a distribution of molecular weights, so if I were to look at all the different molecules within a finished product, we might, and this is indicative, this is not true numbers, we would say that a group 1 might look like this, a group 2 is a little bit narrower, a group 3 is narrower still, and a synthetic PAO is the most regular. So what do I mean by that? Well, because with a crude oil, we begin with a whole soup of different molecules of different types, but also different sizes, we tend to get a distribution. We might have a number of paraffinic molecules of, let's say 10 carbons in length, and we have a number with, let's say 40 carbons, but they're generally around that sort of 25 carbon range. So there's going to be a distribution. Well, because of the PAO manufacturing process, we can get a lot more, we can get that dialed in a lot more. So all the molecules are basically the same size. Now, what that means for volatility and flash point is that you have, let's say, for example, in this box, far fewer molecules that are at those low C numbers. So, like low carbon numbers would be like methane, for example, and he has 1 carbon. So all the gases which are more likely to, if you like, evaporate off. That means that you get lower volatility, but you also get a higher flash point, right? So if you have less volatilization, then it's able to combust less readily. The flip side of that is you also get a lower pour point because you have fewer high molecular weight molecules within your finished lubricant, and that means that you have far less waxy products which raise the pour point. So you get better cold temperature performance. Finally, you also get better oxidation stability. So when you look at the finished product of a PAO, there's very few double carbon bonds. There are no nitrogen or sulfur compounds. There are no aromatic rings. So it inherently has really good oxidation stability, and it's a very strong backbone. One of the other things that I haven't really talked about is you also get better traction coefficient. So I talked a bit about this in the gear oil efficiency video, which I'll link. But that effectively means that because all the molecules are of the same size, the internal friction of that molecule is less. Okay, so the only real downside is that you get lower solubility. With the mineral oils, particularly with group 1s, the fact that there are some polar molecules within the bulk oil means that there is some solubility to it. PAOs are very non-polar, and that can be a challenge for formulators because most additives don't mix in very well with a PAO, and so often you'll need a co-base stock like an ester included in the formulation to actually hold those additives in solution. So I hope that's given you a bit of a background for what the main differences are between a mineral oil as well as a synthetic. I hope this has been really helpful. Again, if you have questions or comments, please leave them in the comment section below. This has been Lubrication Explained.